Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I'm super happy to have Tim Brandt with us today. Hey, Tim.
Hello.
How are you today on this December 10th, 2021, as we do this recording?
Very well, thank you.
Where are you at?
I'm at my office in Santa Barbara.
Yep. Very cool.
Classes, the quarter is over, a little bit of grading left, and then going back to spend the holidays with family.
Awesome. Is that in Santa Barbara or is that somewhere else?
No, that's back out east. The closest family is quite a ways away.
Okay. Well, you'll get a little snow for Christmas or New Year's or whatever it may be.
Yes.
So yeah, actually I was just in Santa Barbara last night. I'm out there at the KITP for the Transport and Stars conference. So I find a little humorous. I was in Santa Barbara last night, and here I've flown back to Phoenix to talk to somebody in Santa Barbara. So all very good. Very cool. So what are you teaching, or did you teach this past quarter?
I did teach, and will be teaching again in the winter, a new course that we are now requiring of our first and second year students. It's an introduction to computing and numerical analysis.
Oh, very cool. Very good.
So students come in with a wide range of backgrounds in computing. Many of them have never written a line of code before. And so it can be a rude awakening if they have to do a little bit of analysis in a lab class or in an upper level class. So we are hoping that this, it's actually a half class, but it gets everybody comfortable at a basic level with writing a line of code, making a plot, doing an integral, doing a few things like that.
That's awesome. That's very good. I just did a video last week with scientific editor Mumdai Rahman on tools you should be using as an astronomer, so coding tools. So we'll put a link to that video below, and you can check out some of the tools that get recommended for coding purposes in classes or otherwise for research. So very cool. Tim, what do you like to do for research?
I tend to be a little bit scattershot in my research interests,
Okay.
but the common theme running through a lot of it is that I like data. This is something that I didn't know about myself initially. I thought I liked other things, but no, it turns out that I keep coming back to data and playing with data and trying to extract as much as possible out of data sets is a theme running through a lot of my work.
Very nice.
And indeed, the paper that we'll talk about today is a tool for exactly this purpose.
Exactly, with a little relationship to exoplanets and otherwise.
Yes.
There. And that is going to bring us to this very lovely AJ article. Orvara, an efficient code to fit orbits using radial velocity, absolute and or relative astrometry. And Tim, take us away.
Thanks very much. And I want to thank all of my co-authors on this who contributed to all different aspects of this paper. Orvara is what it says. It's a tool to fit orbits. And so this paper is a description of the tool. I want to start a little bit with where the idea came from and why we wrote this, because there are other fitting tools out there for orbits. Keplerian orbits have been studied for some time now. And this is, in some sense, one more code. But the reason that we wrote it is because we didn't see something out there that really fit what we needed. It seemed like there was a new niche, and that new niche was brought by a new data set. So the Gaia Satellite has been observing for a few years now, measuring the positions and motions of stars to really remarkable precisions. Something like 10 to the minus 10 radians, I think, if you want to think of it in radians, which is pretty good. With that, we can now measure the orbits of stars as they orbit a common center of mass, not just along the line of sight with radial velocity, but perpendicular to the line of sight in the plane of the sky. A really cool fact is that because Gaia anchors its reference frame to the distant quasars, this is basically motion in an inertial reference frame, just like radial velocity is once you correct for the motion of the sun. So now
Cool.
we have potentially motion this way in an inertial reference frame, motion this way in an inertial reference frame. And we can also measure potentially the separation of the planet or brown dwarf or star or whatever it is if we have imaging. So
Cool.
there are several different data sets, and they should all be described by the same basic math. And we want to be able to fit all of them in a way that is efficient and straightforward. And we didn't have a tool that we could find that really did that for us.
Okay.
The Gaia data set is new, and fitting absolute astrometry has not been as much of a thing until now. People have done it. They've done it for Hipparcos and for a handful of other things. But really combining these different methods in something that was fast and suitable for our purposes didn't seem to exist. And so building on work that Trent Dupuy has been doing for years and years, we decided to try to optimize it and make it a tool that would be useful not just to us, but hopefully to the community at large. And so that's the goal.
Awesome.
There is a GitHub page for this software, so anyone who wants to is certainly welcome to download it. It comes packaged with the absolute astrometry data that is cross-calibrated in the Hipparcos Gaia catalog of accelerations. So everything's packaged together there with some example files. And our hope is that this is something that many people can use.
Nice.
So the paper is going to be a description of this piece of software.
And we will put a link to the GitHub page in the description below the video here.
Thank you. Okay. So I don't think there's anything else I really want to say about the introduction. I think people know what a Keplerian orbit is. They've probably seen it maybe many years ago. Section 2 gives the equations for a Keplerian orbit. And again, I'm not going to go through these. You can find these in any standard celestial mechanics textbook.
Yep.
They've been done for quite some time. The important thing from my perspective here is that you can write down these equations, you can solve them. But then we want to be able to fit a lot of companions because Gaia has data for 100,000 stars overlapping with Hipparcos and the billion stars overall. So being able to do this quickly and efficiently was important to us. So some of these equations, you might be able to solve them more efficiently. You might be able to approach them a little bit differently.
Okay.
And so section 2 is what you would see in probably any celestial mechanics textbook in the initial chapters. Section 3 discusses what we actually did to solve those equations, which is a little bit different in some cases from just plugging into the equations. What were they, 1 through 12, which are the foundational equations.
Right. With equation 2 being where the efficiency is to be gained or not.
The biggest one, yes. Although equations 3 and 4 also, we got a good boost.
Yeah.
But yes, equation 2 is very, very famous. It's known as Kepler's equation. And in fact, there's a book on solving it over 2 centuries or 3 centuries, a long time. So for this, one thing that surprised me a little bit was that solving Kepler's equation actually was a limiting step in the code. It initially took most of the time. And so I spent quite some time trying to think about ways that we could speed it up through some combination of lookup tables or some other tricks before finally stumbling on a paper by a co-author on this one, Virginia Raposo Pulido, who wrote a paper that got far less attention than it deserved a couple of years ago. It only has a couple of citations with an approach to do this, to solve this equation in a way that I would say is not quite iterative, because it starts with a very good guess for the solution, but then that guess is so good that you can guarantee that in a single step, of Newton-Raphson or a higher order analog, you
Yeah.
can get to an acceptable accuracy.
Nice. Okay.
The usual approach to solving Kepler's equation is you get a guess that is decent, and then you do Newton-Raphson until you're satisfied.
Yes.
And satisfied could mean anything you want. It could mean a tolerance of 10 to the minus 5, single precision floating point. It could mean anything.
Right.
So what we try to do here is to implement a solver that gets you essentially to double precision floating point accuracy within a factor of a couple. And that within a factor of a couple is important because that means we're not bound by the machine precision requirements that you must have the right answer down to the last decimal place.
Okay.
If you're willing to give that factor of a couple, it allows you to use series expansions for trig functions that you might not otherwise be able to use. And it allows you to use a certain definite number of steps of a Newton-Raphson iteration. So the basic idea here is that we fit piecewise polynomials, a piecewise quintic, to the eccentric anomaly as a function of the mean anomaly.
Okay.
It's defined at certain points where we can know the answer, and then we can compute the coefficients of this polynomial. The coefficients do depend on the eccentricity, and so for each orbit, you do need to recompute them. That does have some computational cost, but in practice, it's not that large. The fact that you need to compute these once for every new eccentricity means that there is some overhead for each new orbit. And if you're just computing a single point for the eccentric anomaly, then it takes about twice as long per point as if you're computing many points. So this approach is still much faster than anything else we've been able to find, but not quite as fast as if you're computing many points. In our case, we usually are computing many points because we're tracing out an orbit with a lot of measured data sets. So we define this quintic polynomial, and that gives us the initial guess for a few floating point operations.
Okay.
And then a single step of Newton-Raphson or a higher order analog brings us to essentially double precision floating point. So if you go down to the first figure, this just shows that we're doing well up to very, very high eccentricities, where we're in fact limited by round off error in Kepler's equation itself. It's something that you just can't get around at those eccentricities unless you do a series expansion and think about the orbit in some other way. In practice, we're going to be limited by the precision at which we can measure the time of the observation, so it's irrelevant.
Yeah, okay, fair enough.
So these absolute errors here are basically double precision floating point precision. Slightly worse, again, as you get to very high eccentricities, but that's a feature of Kepler's equation, not the solver. And on the right, it shows that we are indeed doing pretty well on this, that if we have a lot of points in an orbit, then the computational cost of getting the eccentric anomaly and sine E and cosine E, all of which we need to compute an orbit, is actually about the same or even a little bit less than just computing sine and cosine. So the trick to get E, sine E, and cosine E more cheaply than sine E and cosine E is because we don't have quite the same accuracy requirements. We can be a factor of a couple worse, but still a factor of a couple worse, 10 to the minus 15, 10 to the minus 16. It's not relevant for these calculations. So
good.
We have a couple of other computational efficiencies. One is that by refactoring the radial velocity, we can avoid some trig calls and speed that up. And in the end, the eccentric anomaly still takes something like half of the total time, but we've beaten it down enough that this approach works much faster than others. And this solver is now also implemented in Dan Foreman-Mackey's exoplanet package, and we'll see about getting it in some others.
Yes, and this one, Goatherd, this one came out not too long ago.
Yes.
It was a little different approach. It was a integral approach.
Yes.
Right.
Yes. So I think that's pretty much what I wanted to say about the implementation there. The next step is pretty much a straightforward likelihood calculation
Okay.
where we're skipping now, I believe, to section 4.
Yes, we're just talking a little bit about those trig identities you mentioned.
Yes.
Projections and likelihoods.
Yes. Oh, I do want to say a couple words about multiple companions.
Yeah.
Section 3.4.
Yeah, that should be mentioned.
Yes. A Keplerian orbit is the two-body solution.
Right.
In many cases, you have more than one planet, or you have an outer star or something like this.
Mhm.
To really do it properly, you need a full n-body approach.
Yes.
The three-body problem famously doesn't have an analytic solution.
Yep.
But that is very much not in keeping with this spirit. And so if we want to be able to fit Keplerian orbits to more than one companion, you need to make some approximation.
Yep.
In radial velocities, you usually just think of it as the superposition of several Keplerian orbits on top of one another. And the star follows the orbit from all of them together.
Mhm.
We use that same basic approach, but there are a couple of subtleties that we need to account for. One of them is that the motion of the star, yes, will basically be the superposition of its motion due to all of the companions. But if you're measuring a relative position between the star and an outer planet, for example,
Okay.
then the motion of a star around its center of mass with an inner planet can matter.
Yes.
And it does in some cases, some applications that we've dealt with.
Mhm.
And so our approach is to account for that in the superposition of these orbits. So if we have an outer companion, then we view the inner system as a single mass
Okay.
with its mass equal to the combined mass of all the components
Uh-huh.
located at its barycenter.
Yes.
And then we solve for that orbit.
Okay.
And then on top of that, we resolve the inner orbits, and we do it in a nested way. We
Okay.
verified that this does give something very close to the right answer. It's not perfect, but it's much, much better than
And body. So it's a sequence of nested two-body solves.
that's right.
Yep, I'm with you.
Okay. So then the likelihood, we're just going to do a classic likelihood approach here,
Yeah.
where we write down the log likelihood as chi-squared, and that is going to have components from the radial velocity, the relative astrometry, and the absolute astrometry.
Mhm.
And you can write all of those things down
Yes.
and then feed it to Markov chain Monte Carlo.
Okay.
When you write down that likelihood, we play a couple more tricks in an effort to make this work more efficiently. So for example, with the radial velocity, you can write down that likelihood as just the radial velocity minus that you predict minus the one you expect squared over the uncertainty squared,
Right.
with a jitter term thrown in
Mhm.
as is standard practice.
Mhm.
But you don't know what the instrumental offset is, or another way of saying this, you don't know what the systemic radial velocity of the system is, what the barycenter radial velocity is.
Right.
And that is that ZP in that equation,
Okay.
which is often referred to as the 0 point.
Point. Mhm. Yep.
If you exponentiate that in equation 26, that turns out to give you a likelihood that is just Gaussian in the 0 point.
Uh-huh.
And
Yeah.
so if the 0 point isn't something you're really interested in and you just want to get rid of it, you can do that integral analytically.
Okay.
And so for any number of instruments, you can simply integrate the likelihood and marginalize out the radial velocity 0 points. So that means your Markov chain Monte Carlo has fewer parameters it has to optimize over. These are taken out exactly.
Okay.
And so it's even better than sampling over them because you have done the full integral, you've accounted for them properly.
Yep. Gotcha.
So we can also do something similar to that with the absolute astrometry. So
Mhm.
equations 28 through 30 are just going through the that marginalization. It doesn't actually cost you much computationally.
Yeah, a couple of squares and a divide. Okay.
For the astrometry,
Mm-hmm.
you again have nuisance parameters. You don't know what the motion of the system barycenter is across the sky. And in some sense, you don't care at this level of precision, whether it's 137 or 137.3 in this direction, milliarc seconds per year, doesn't matter. So you would like to be able to integrate that out too and get rid of that nuisance parameter also.
Okay.
The math becomes a little bit more painful, but
Yeah.
it is still doable. And again, it doesn't add significantly to the computational time of computing the likelihood.
Okay.
So computing the likelihood remains less expensive than computing the orbit. If we are willing to adopt the Gaia measurement as our prior on the parallax, we can also marginalize out the parallax.
Okay. Mm-hmm.
So all the
Okay.
0 points, the barycenter proper motion, and the parallax,
Yep.
that's 4 or more parameters, depending on how many radial velocity instruments you have,
Okay.
we can take care of and marginalize out exactly just by doing the integral.
Mm-hmm.
So the appendix has some more details on how we actually do that. But we take it out, and then it makes the Markov chain Monte Carlo's effort a little bit easier.
Okay. Okay, good. Yes. And
Yes.
yeah.
One other thing that we can actually do, as indicated by equation 33, is that sometimes
Is that one?
you have a star and you might have a companion around it, and then you have another star. So you have a system like that, what we would call an S-type planet. And if you have that outer companion, it may be that both stars are detected in Gaia, and so Gaia can measure a relative proper motion for both of them.
Mm-hmm.
This can be handled in the exact same framework. Again, the math gets a little bit messy. But if both stars are present in Gaia, then you can include the proper motion measurements for both of them when you are doing your fit and the separation for both of them.
Nice.
So that's something that we've applied for a subset of our analyses, is ones where there are 3 bodies in the system, or however many. You have information for the central star, you have an indication of a companion around it, and then you have an outer body with a proper motion measurement, and we can include that. So the marginalized likelihood explicitly does marginalize over these things. It still leaves us with a lot of parameters that we cannot analytically marginalize over. So there are the Keplerian orbital elements, the mass of the primary and the secondary, and we're still going, and the RV jitter, and we're still going to have to constrain those, and we resort to Markov chain Monte Carlo for that.
Okay.
So that's basically how the code actually works. And if you want to use it, you can download it from the GitHub page. You can install it. We've tested it on a variety of systems.
Here we go.
And yep, if it works for you, that's fantastic. If it doesn't work for you, we want to hear about it.
Hear about it. Exactly. That's right.
So once you have your code installed, then you can fit some data. In order to fit data, the code is going to take a configuration file. We supply some examples, but that lets you specify things like what the Hipparcos identification of the star is in order to look up the absolute astrometry. It lets you specify the files where you have radial velocities, if you have any, or the files where you have the astrometry measurements, again, if you have any. If there are some data sets, data types that are missing, that's fine too, and it will fit whatever it has. So once you set up this configuration file and you click go and you run, then you end up with a Markov chain, a whole bunch of sets of parameters that are hopefully sampled from the posterior distributions. The code also comes with some routines to make plots and to visualize these, with a goal of having it be relatively straightforward to make publication quality plots.
Oh,
So the configuration file is described in the table, and the plots from there is the format for the input data files, just for reference, and then there
yes.
will be
Not sure.
Yep.
Mhm.
So you can specify if you have different instruments that you used for your radial velocities, and you can specify if you observed different companions in relative astrometry, if there are more than one image companion, for example, or if you have a brown dwarf and then an outer star, then there would be more than one companion with entries in the relative astrometry data
Right.
file.
Right. Okay. I'm with you.
You can then, with this chain, you can make some plots. So let's skip down to the plots.
The orbits.
You can pause briefly here. This is a description of the configuration file. Might be a little bit daunting, but there are example files supplied with the code.
Good.
So those can get you started.
Good. All right.
And then,
Oh, it's good to be very explicit here on. I like this. This is nice. This is good. Super. Okay.
and then here are some of the plots that it is configured to make for you. So for this, we used as an example a white dwarf orbiting a main sequence star.
Like those.
White dwarfs are nice for this purpose because they're massive, so they make the star wobble a lot, and they are faint, so they don't screw up your astrometry measurements of the star, and so that you can trust the absolute astrometry.
Good.
So it makes for these orbits that turn out to be very well constrained. And you can maybe see from that color bar that the uncertainty in the mass is extremely low, perhaps surprisingly low given the range of orbits that seem to be permitted. The intuition for why the mass is so well constrained, even though the orbits might be a little bit fuzzy, is because between the absolute astrometry and the relative astrometry, you're measuring a 3D acceleration in an inertial reference frame.
Okay.
Which is just GM over R squared. No reduced mass, no nothing, just mass.
And
if you combine that with a measurement of the separation, then you get R. You can actually solve the three equations for the mass and for an angle.
Cool.
So we get extremely precise masses, and we can visualize the orbits then color-coded by mass. The files to make these plots are distributed with the code. If you go to the right a little bit, we provide two different ways to color code your orbits, coloring them either by eccentricity,
yes,
or by companion mass. And if you have more than one companion, you would pick one, which you can designate in the configuration file.
Okay.
The plot on the right is a prediction of where you expect the companion to be at a certain time.
Yes.
This has proven useful to us if we want to look for something that we think is around a star, but we haven't imaged it yet. Or if we want to do some kind of calibration of an instrument or something. So if you have a radial velocity trend, or a good fraction of a radial velocity orbit, and you have the absolute astrometry measurement, you might be able to constrain the full three-dimensional orbit even before you've imaged it. And so then you could predict a companion's location before you go out and look for it, kind of like was done with Neptune. So in this way, you can predict future locations and see whether this companion is something that you could possibly image with an eye towards substellar companions.
Cool. One question on this plot. So the dashed line here is probably a line of nodes.
Yep.
Yes, and then the less dotted line, I guess I would call it. What is that?
I believe it points to periastrum, but I don't recall.
That would make sense. That would make some sense. Let's see if we got it in here. Dash line align nodes, good for me. Circles.
Dotted lines connect the host star to periastron, yes.
Yeah, okay.
And those are given for the black line, which is the maximum likelihood orbit. The
Okay.
other colorful lines are just randomly drawn from the posterior.
Mhm.
Give you a sense of what it looks like.
Of the spread of it. Okay, I'm with you. Good. Awesome.
So these plots you can make with a single command once you have your file configured, and it will just write them out for you. There are a couple more plots on the next page.
Ooh.
So these show the radial velocity curves, again, color-coded in the same way.
Mm-hmm.
And if you have more than one instrument, in this case, all the radial velocities are from a single instrument. I believe it was high res. If you have more than one, then they'll be drawn with different colors.
Okay. Very good.
In this case, the data are very good.
Yeah.
The trend is large. And so in the upper plot, you can't really see the uncertainties.
Right. Right. Here we do. These are the residuals down here. Uh-huh.
Yep.
Very cool. Very nice. Very
And
nice.
then if you, there's one more, I believe one more set of plots on the next page.
Uh-huh. Proclamation.
Two more sets of plots.
Ooh, this is a bigger one.
So
okay. Ooh, it's definitely a bigger
no,
one.
this is it. Okay. So the separation and position angle. The first plot showed the orbit in the plane of the sky.
Mm-hmm.
This simply shows it broken down in separation and position angle.
Okay. Yes, got it. Separation epoch, position angle, residuals. Good. Awesome. The same system. Nope, the other part. Ooh, proper motion.
And then the bottom two are proper motion.
Yeah, proper motion.
So in this case,
deck. Yep.
there are 3 proper motion measurements, and that should be true for any of the stars in Hipparcos and Gaia. The measurements are Hipparcos proper motion, Gaia proper motion, and then the difference in position between Hipparcos and Gaia. So this is an average proper motion,
Okay.
some kind of an integral over the proper motion.
Uh-huh. I'm with you.
That average proper motion is not shown in these plots,
Mhm.
but it provides an integral constraint, and that explains why the curves are so narrow and so bunched up.
Right.
Because they must follow that constraint, even though it's not explicitly plotted. Given that it's an integral constraint, I'm not sure quite how to show it in this framework. Could show it in a different kind of framework if you wanted to.
Yeah.
If you want to check and see whether your fit is reasonable, you can also check your chi-squared values for these proper motions.
Okay.
So the code does print these out for the best fit orbit if you ask it to. And you can make sure that your chi-squared values for the proper motions are, let's say, no more than a few,
Yes.
which would suggest a reasonably good fit. If your chi-squared values for the proper motion are high, or for anything are high, then that suggests that you were not able to get a good fit to your data. So something about your data or your model isn't right, whether it's an additional companion in the system or unmodeled systematics in your data.
Right. Very nice. Very cool.
The last couple of tables here include the constraints on the properties. It gives you your priors. You do have some freedom to set your priors in the code. Not a ton, but some.
You have a choice.
The ones that are relatively straightforward to set yourself are in the primary mass and the secondary mass. So we do provide interfaces to change those two. The others are more hard-coded, where you can change them if you really want to, but it is not so straightforward to do so.
Okay. Okay. All right.
Okay.
Good.
So then we applied the code to this particular system, which is a pretty cool system. It's a white dwarf around a main sequence star in a moderately eccentric orbit, not too eccentric. We were able to get a very precise mass in orbit, and rule out a scenario in which the two bodies were close together in the past.
Ooh.
And so this suggests that the system represents kind of vanilla single star evolution for the white dwarf, for what is now the white dwarf.
Uh-huh.
This lists the parameters that we fit. And if you want to make a table like this, the code gives you the option to output something in pseudo LaTeX format. So it should be pretty straightforward to make something along these lines, including these fitted and derived parameters. The final figure in the paper is the resulting corner plot, which again, the code will make for you if you would like it to. And it will make it for you with these physically motivated parameters: the inclination, eccentricity, semi-major axis, and the masses of the two components. So by default, it doesn't plot the other parameters, although if you wanted to, you could plot them yourselves. Your chains are going to be saved as fits files in a fits table format. And so I think that's basically the code. It's a tool.
It's a tool, yeah.
Hopefully a useful one. We've used it now in a series of papers, and we're using it all the time to derive masses for companions that previously only had M sin I measurements, and to try to see which companions might be accessible to direct imaging if we're trying to find new planets and brown dwarfs that are exerting detectable influences on their host stars but have not yet been imaged. And again, it's on the GitHub page. Please, if you are interested, go ahead, download, install it, run the tests, run the sample files provided, and hopefully you'll be able to get something useful out of it with your favorite systems.
Very cool. Very nice. So, one, thank you very much for walking us through this very lovely paper on orvara. And B, thank you very much for sharing it with the community, making it open source. I'm a big proponent of that.
Yes.
So let me then ask, so what is the, where do we go from here given the published work? Anybody who does software knows by the time that you've probably published the paper, it's already out of date relative to what's on repo. So do you imagine an orvara 2 and orvara 3? So where might you be headed with code development, or as the community uses it and gives you input on, where does the community need the code to go? And are there additional science applications that might be coming from, or that the code can handle? Is there stuff from JWST or VRO or things along that?
There are a couple of science applications that are less common now, but that we are implementing and intend to implement soon.
Okay.
So one example is that occasionally you might have measurements of the relative radial velocity between a star and a planet or two stars. You might want to incorporate that relative radial velocity into the fit.
Okay.
So that is something that I believe we just pushed that onto the master. I believe it is implemented now. If not, it will be very shortly. Okay. Next, right now it uses those three proper motions as cross-calibrated in the Hipparcos Gaia catalog. Gaia full DR3 will be out in around 6 months. And that is going to give additional measurements, not just the proper motion from Gaia, but accelerations from Gaia.
Nice. Yes.
These additional measurements, once we've cross-calibrated them and are confident in the precisions and uncertainties, will help to constrain orbits. And so that is another thing that we intend to have implemented on the timescale of Gaia DR3. Nice. My best guess is that our first step will be to calibrate these and make sure that they're on the same frame, we trust them, etc. I imagine the Gaia team will do a lot of this with their own preparation and processing of the data.
Right.
And then actually implementing them in the software should be straightforward enough that we'll be able to do it around the time that Gaia DR3 comes out.
Mhm.
So those are the two new applications that I have in mind. And the other ones, I don't have them in mind right now, but I'm certainly always interested in where people would like this to go.
Yeah. And so if you do have a comment, you can probably put it on the GitHub repo somewhere.
Yeah.
If there's an issue or a comment, or send just an email to
Yes.
Tim. That works too. Very cool. Tim, thank you so much once again for walking us through this lovely tool, new tool. And that'll do, everyone. And I hope this made your astronomy day just a little bit better, and we will see you on the next one. Bye-bye.
Thank you.